All right, so last week was dedicated pretty much all to graphing, and we took kind of an extra day on Friday to go over graphing and have some time to work on that. But at this point, we're going to move on to acceleration. And when we do our lab on acceleration, that one will involve velocity versus time graphs. So there'll still be some graphing here and there. Okay, but we're not going to be spending a whole lot of time on just graphing anymore. Okay, we'll just be looking at acceleration and then vector addition from there. So what we're going to go over today is some of it's going to be a review, and some of it's going to be new. Okay, you learned what acceleration was in Science 10. You learned one acceleration formula in Science 10. And you learned about acceleration being part of a velocity versus time graph, and that's kind of where it ends. So we're going to go over that stuff again, and then we're going to learn the rest of the formulas that we'll be using for acceleration. Because acceleration is a big part of Unit 1, especially when we get to projectile motion. And it's a huge part of Unit 2, where we're dealing with forces that cause objects to accelerate. So we're going to be coming back to this idea of acceleration and problem solving to do with acceleration quite often. Okay, so first off, what is accelerated motion? If something's accelerating, what's happening to it? Could be getting faster, could be getting slower. In either case, what is changing? Right. Speed or velocity would be kind of more technically correct. But yeah, if there's a change in velocity, then there's an acceleration that is going on. Right? So any change in velocity is acceleration. Right? We've got to look at the relationships between velocity, distance or displacement, time, and acceleration. Right? So we're looking at that. Acceleration is a vector quantity, so direction is important when we're dealing with that. And then obviously be able to solve accelerated motion problems. So that'll be kind of a bunch of the new formulas that we're going to learn. All right, so whenever the velocity of an object is changing, the object is accelerating. That is the definition of acceleration. Any change in velocity over time is an acceleration. Okay? Now, there's different types of acceleration. There's uniform acceleration, which means that the velocity changes at a fixed rate. And then there's non-uniform acceleration, where the velocity is changing at a non-uniform, or it's changing at a different rate all the time, okay, which will result in a curve. We don't really deal with that in Physics 20. So we'll be dealing mostly with uniform acceleration, right? So a good example of uniform acceleration would be a plane taking off on a runway. A really bad example of uniform acceleration would be a car accelerating away from a light. Okay? Why is a car accelerating away from a light a bad example, but a plane a good one?
A plane is going at a constant, it's accelerated up to a certain point of speed. Whereas a car, there's other things you take into factor, like the road or people driving. Okay,
you could, yeah, there's kind of other factors sometimes with a car. Let's say I put them both on the runway, the tarmac, side by side. Okay, so I kind of take all of that other stuff that you mentioned, which is good, out of play. What does a car have to do that a plane doesn't?
Stay on the road.
Well, no, a plane better stay on the tarmac. If it goes off, it's gonna be bad, right? If it goes off the runway.
Oh, I mean like taking off.
Oh, okay. I just mean the before it lifts off.
Oh.
So they're racing. Let's see, they're racing a car and a plane side by side. Okay. What does a car have to do the plane doesn't?
Change through gears?
Exactly. Change through gears. Okay? A car, when it accelerates, its graph actually looks like this. It's very non-uniform, right? It's a curve. It's got each gear accelerates slower than the gear before, right? It's why if you're going to pass somebody on the highway, when you mash the accelerator down to the floor, your car switches gears, right? Back when you actually had to shift gears manually. Can anyone drive a stand? Wow, I think that is the biggest number I have had in a long time, okay? Because most people now, they're like, oh, what now? Yeah, some cars used to have 3 pedals. Clutch, and brake, and gas, okay? Yeah, so when you had to shift gears manually, okay, you would, if you were gonna pass somebody, you didn't just press down on the accelerator, because you'd die, okay? When you were in 5th or 6th or whatever, if you pressed the accelerator, your car did this like really lethargic kind of, and it would try to accelerate, but the gearing was just wrong, okay? That's your fuel economy gear. It's not for passing. So you would, if you were in 6th, sometimes you'd just skip 5th and go right back to 4th, okay? In order to get enough jam to get around somebody. In an automatic, just pressing the accelerator will automatically shift down, okay, and get you a gear that accelerates better, but it's not uniform. A plane doesn't have gears. Right? And until it puts the flaps down to create lift, which it doesn't do until it reaches a certain speed, okay, it accelerates very uniformly because it doesn't have any gears. They just push the throttles forward and that's it. Okay? It just accelerates. Does everyone kind of follow the difference? Now, last year, you would have learned this formula here. Okay? That acceleration is a change in velocity, that's this part here, divided by time. Okay, so delta V, change, right? Delta means final minus initial, over time. All right, so that's the one you would have learned last year. Okay, you learned how to manipulate that and use it in previous. All right, everybody all right with a quick review of what acceleration is? So, easy example of acceleration here. So let's say we've got this plane. It starts from rest. Okay, is that an important term to know? If you are at rest, what are you not doing? Right, you are not moving. So anytime a question says starts from rest, or sometimes they say comes to rest, it means that one or the other of your velocities is 0. Starts from rest means VI is 0. Comes to rest means, yeah, it comes to a stop. So VF, your final velocity, would be 0 in that case. So anytime you see the word rest, something is at 0 meters per second. Okay? The plane accelerates down the runway, and at time 29 seconds is at a velocity of 72.2 meters per second, positive, okay, where the plus sign indicates to the right. Okay, determine the average acceleration of the plane. So anytime we're solving a problem in physics, well, we want to write down our givens. So the first thing they told us was VI is 0 meters per second. Okay, they told me VF was 72.2 meters per second, and that was a positive value. They told me that that took 29 seconds. All right, those are my givens. Here's why writing down your givens is A, worth a mark, and B, a really good idea. You are going to have 5 different acceleration formulas. Writing down your givens will help you to determine which one you should use. Okay? In this one here, I have VI, VF, T, and I'm looking for A. So I only have one formula on my formula sheet that has those 4 things in it, and it's the one we learned last year in Science 10. This one here. Okay. Do I need to manipulate it? It's already set up to find what they asked me to find, right, which is A. So all I have to do is plug in my numbers. So acceleration will be 72.2 minus 0 divided by 29 seconds. Okay. When I punch this into my calculator, what do I have to make sure happens? Okay. If I punch that into my calculator, in the order I have it written, what's it going to do first? It's going to divide, right? Okay, that's not what I want it to do. Okay. Not cool. I don't want that. Okay, so I have to make sure that I'm actually going 72 divided by 29. I have to make sure that the top is done before the bottom. Okay, 72 divided by 29. Okay, that's much better. Okay, 2.5 meters per second squared. Okay, or meters per second All right, is that ringing a bell, that formula? Okay, so that's what we just did there. Okay, we just put in our numbers, but we made sure we did the top before we divided by the bottom, because it is the change in velocity divided by the change in time, and we need to reflect that in our calculations. Okay, so the velocity of the plane changes by 2.5 meters per second every second. That's a pretty good rate of acceleration, considering gravity is 9.81. Okay? And when you fall, you accelerate pretty fast. All right, here's the other formulas that we're going to learn about today. Okay, we're going to learn about this one here, which calculates displacement using VI times t plus 1/2 AT squared. Okay, where this formula comes from is from your velocity versus time graph. So if I have an object that's accelerating and I get a graph that looks like this, this formula calculates displacement by doing this. That bottom part will be the height of the rectangle, VI, my initial velocity, times time, so it calculates the area of the rectangle, and this part calculates the area of the triangle. So it calculates displacement. Now it can be used to calculate lots of other things too. Okay? It could calculate VI, it can calculate T, it can calculate acceleration. It all depends on what you're given. Now its counterpart, which looks very similar, okay, VF times T minus 1/2 AT squared. So what that one is doing, same graph, okay, but what it's doing is saying, all right, here's VF up here. It's going to multiply VF by T and calculate this whole rectangle. And then it's going to subtract this part. Does that give me the same area? Okay, if I take this whole box and I subtract this part here, right, and I subtract this part, doesn't that leave me with this? It does. Okay, it's just looking at it from a different perspective, but it's calculating exactly the same thing. And so where one is using your starting velocity, the other is using your final velocity. Right, they calculate the same thing. Okay, VF squared equals VI squared plus 2AD. Okay, not really to do with graphing as much. Okay, that one's going to be used a lot in projectile motion, and we'll talk about that one in a bit. And then there's this one here at the bottom, which you've actually already seen before. Okay, if the acceleration is uniform, I can use this formula. If it's not, then I can't, because here's what this one's really doing. VF plus VI over 2. What is that likely to be calculating? What am I calculating when I add two things together and divide by 2? Their average, which is fine as long as the progression between the two is constant. Okay? Because then really what I'm doing is finding the halfway point. So really all this formula is that one. Just written slightly different. Right? The only qualification on that one is the question has to outright say, this object is undergoing uniform acceleration. Then you can use that one. If it doesn't say that, no guarantee it'll work. All right, so we're just going to look over a bunch of examples here today, look at how we manipulate all of these formulas and kind of get used to how they work. Okay. I want you guys to write that one down. See if you can figure out which formula to use and then solve it. Give you a couple minutes, then I'll walk through. Whoa. First step, write down what we're given. So it says a hybrid car with an initial velocity of 10 meters per second east. All right, so right there they gave me VI, 10.0 meters per second east. It accelerates at 3.0 meters per second squared east. So they gave me acceleration. How long will it take, that means find time, okay, to acquire a final velocity of 25 meters per second east? Okay, so everything's east, so direction's not going to be a factor here. I don't have to worry about positives and negatives. This is all in a straight line. Okay? So I have VI, VF, A, and I'm looking for T. So that means I'm going to use this formula, because it's the only one that has those four things in it. But now I'm looking for time. So if I'm going to get time by itself, what do I have to do? Multiply. Yeah, we got to multiply both sides by time. So time comes over here, and then I got to get rid of A. So I'm going to divide both sides by A, and A ends up over here. So my final formula is T equals VF minus VI over A. Now all I have to do is plug in my numbers and solve. So my final velocity was 25, my initial velocity was 10, and that's over 3. Okay? 15 over 3. Okay? 5.0 seconds. 2 significant figures, because that 3.0 only had 2. Okay? Do I need a direction on that? No, time is scalar. I don't need a direction on that. What's that? Okay, ringing a bell from last year, I would have asked you to do ones just like that in Science 10 physics. All right, I want you guys to try those two, but there's a trick here. Okay. In the second one, they give you the velocities in kilometers per hour, but they give you the acceleration in meters per second squared and the time in seconds. Can I use those as they appear there? No, I cannot divide kilometers per hour by meters per second squared or by seconds. The time units don't match, the distance units don't match. So I will have to do a compound conversion. First, you try number 1, then I'll walk you through compound conversions, and you can try question number 2. Okay, let's work on number 1 first, and then we'll try 2. All right, so for number 1, okay, our givens are initial velocity, 6 meters per second east. Okay, we're given acceleration, 4 meters per second squared east. Looking for how long it'll take, so it's just like the example we just did. And our final velocity is 36 meters per second east. All right, so acceleration equals VF minus VI over T. That's the formula I have to use because it's the only one I have all the information for. I'm solving for time, so I'm going to multiply both sides by time, divide both sides by A, and be left with this. And then just plug in my numbers. 36 minus 6, okay, divided by 4. All right, so we're going to have 30 over 4, which should give us 7.5 seconds. Okay, again, no direction on that because time is scalar. All right, I have to make sure, though, when I punch this into my calculator, that I'm doing the top first and then dividing by the bottom. The formula is change in velocity divided by change in time. Okay? And if you don't punch it into your calculator that way, it'll do order of operations and it'll really mess it up. All right, questions on the first one? Okay, then we got to talk about compound conversions because this comes up sometimes. So, I mean, if all I had to do was change the kilometers to meters, that would be easy. The only thing I had to do is convert hours to seconds. That would be easy too. It's a single conversion. But I have to change both, right? Which means I'm actually just going to do 2 single conversions, but all in kind of one step. Okay? So I start out with kilometers over hours. And I'm wanting to get that to meters per second. So I'm going to convert each part of this separately. What would I have to multiply by in order to get kilometers turned into meters? What does kilo mean? It means 1,000. Doesn't matter what units we're in. That's the beauty of the metric system. Okay, same prefixes every unit. Kilo always means 1,000. All right, that's why we say if you won $10,000, you won 10K. Kilo. Okay, 10,000. All right. So in 1 kilometer, there are 1,000 meters. That's my conversion factor. Okay. I also have to convert hours to seconds. So in 1 hour, notice I'm putting the hours on the top, okay? Whatever I'm trying to get rid of, I'm putting opposite so that it cancels out when I multiply, okay? How many seconds in 1 hour? Everybody, that's the knee-jerk reaction. 60! 60! I know the answer. 60. No, it's not. It's 60 times 60, which is 3,600 seconds. All right, so when I multiply all this through, because I'm not saying like do this every single time, I'm going to show you kind of the shortcut here in just a second. Okay, so I would take whatever this number in kilometers per hour was, for this question it's 20, okay, and I would multiply it by 1,000, and then I would divide it by 3,600. And what would happen would be the kilometers would cancel, the hours would cancel, and I'd be left with meters over seconds, which is what I'm looking for. But I don't want to have to do 2 steps like that. Okay? If I'm multiplying this number by this and then dividing by this, what I'm really doing is taking my kilometers per hour, not equals, and multiplying by 1,000 over 3,600, which I can simplify to this. 1 over 3.6. What's anything times 1? Itself. So really, all I have to do is go kilometers per hour divided by 3.6. And I'll get meters per second. The same is true, well, not exactly the same, but it's similar going the other way. Instead of multiplying, instead of dividing, I would, spoiler alert, multiply. So if I was given meters per second and had to go to kilometers per hour, I'd multiply by 3.6, okay? And I'd get kilometers per hour. All right, that's how we do a compound conversion. Put both sets of units up there. This is the shortcut. Just remember 3.6. Okay, we do this one often enough that it's worth remembering. Kilometers per hour to meters per second, divide by 3.6. Other way, multiply by 3.6. All right, so you're going to have to convert the kilometers per hour 2 meters per second using that method, and then at the end convert back to kilometers per hour. Okay, I'll give you a couple minutes on number 2. You have to do a bit of manipulating. Okay, so for number 2, the first thing we have to do is do our conversions as we write down our givens. So they're telling us the initial velocity is 20 kilometers per hour. So if we divide that by 3.6, okay, we're getting 5.5 repeating, okay, as our initial velocity in meters per second, and that's north. Okay, it accelerates at 1.5 meters per second squared north. Okay, for 9.3 seconds until it reaches its final velocity, which is what they want us to calculate. Okay, that means I'm going to have to manipulate this formula. Okay, and I do have to use this formula if I want to solve it in one step, because it's the only one that has that pieces of information in it. All right, so I'm trying to solve for VF. So if I follow my rules of algebra, I'd want to move what's not attached to VF first. And what's not attached to VF is T. So I'm going to multiply both sides by T. Now it's over there. And then what am I going to do with VI? Add it over to the other side. Now that should make sense. T times A calculates the change in velocity. So if I take VI, my initial velocity, and add the change in velocity, that should give me my final velocity. Okay? So VI plus T times A equals VF. So if I plug in my numbers, that's going to be 5.5 repeating, okay, plus 9.3 times 1.5. This one you don't have to worry about order of operations. It's going to do it right no matter how you punch it into your calculator. Okay, so I'm going to take that number and I'm going to not try and type it in again. I'm just going to use it. Okay, plus 9.3 times 1.5. That way I preserve all the decimal places. Okay, so that's going to give me a final velocity of 19.5 meters per second north, but they want it in kilometers per hour, so I got to multiply by 3.6, and that'll give me my 70 kilometers per hour. Okay. All right, now, we did not see, there's one manipulation of this formula now that we haven't seen, so let's quickly go over that, okay, just in case anybody's wondering. What if I want to solve for VI? Okay. If it were me, I would do it this way, right? And here's the reason why. Okay, a lot of people will leave VI over here and forget that if they leave VI here, it's going to be what? Negative. I always forget that. I hate solving for a negative because I always forget and then I get the vector wrong on my answer. Okay, so the first thing I'm going to do is multiply both sides by t, just like I did here, and then I'm going to add VI. Okay. Now, you're probably looking at that and going, yay, Coder, you just solved for the thing you don't want. You're solving for VI here. Yes, I am. Now, what can I do with t times a?
Just get rid of the x somehow, so you have to maybe times it by.
Well, I don't want to do any multiplying, okay? I just want to get VI by itself. Now, if we're thinking order of operations, would I multiply these two numbers together before I add it? I would, right? So this is really just one number. Can I subtract it over to the other side? For sure I can. Okay, so that's what I'm going to do. I'm going to subtract t times a over here. Okay, that's going to leave me with VI. Okay, it's the opposite of what we had here, right? We said VI plus t times a equals VF. So logically speaking, VF minus t times a should give me VI. Okay, everybody all right with that idea? Okay, so there's how we manipulate that formula. Okay, shows you all of the manipulations for that formula. Please don't make this mistake, because I've seen people do this. They write down all the manipulations on their formula sheet. And then on their exam, when they don't get to use their formula sheet, they're really screwed because they don't know how to manipulate anything. Don't do that. You don't want to end up that person. Okay? If you're having trouble with the algebra, come and see me, and we can work on that together. All right, any other questions on that first formula? Okay, hopefully that's ringing a bell because that's stuff we would have done in Science 10. Okay. I want you to write this example down, and then we're going to walk through it. All right, so a big part of problem solving in physics is, believe it or not, reading comprehension. Okay? But it's not like in English where you have to find the hidden meaning, but there's no hidden meaning. Okay? As long as you understand what's going on in the question, we're very forthcoming about what we mean. Okay? It's not, when we say that they're like a red, red rose, that they mean something else. Okay? They're a red rose. That's what we mean. Okay? A cattle train is traveling west at 16 meters per second. All right, what did they probably just give me there? Within the context of this question, yeah? Nope, not acceleration. Yeah, which one? Okay. Initial, right? This is what it's doing. At the beginning of the question, this is what it's doing, right? So our initial velocity is 16.0 meters per second, and it's west, right? That's what the cattle train is doing. Then it says it's brought to rest. So at the end of this question, how fast is it going? 0. So what did they just tell me there? Final velocity. Okay, and it takes 8 seconds to do that. Find the displacement of the cattle train while it is coming to a stop. And then there's these keywords. Assume uniform acceleration, which formula should I use here? Garrett?
D equals VI plus VF divided by 2 times by T.
Yep, I should definitely use that formula. This is an accelerating object, and I'm not given or asked for the acceleration. Weird, okay? Really, really weird. So I gotta use the weird formula. You know, that one I told you can only use if the question explicitly states uniform acceleration, which this one does. Now, do I have to manipulate this at all? In this case, I don't. It's already set up to calculate displacement, so all I have to do are plug in my numbers. So VF, we were told was 0. VI, we were told was 16, okay, over 2, and then multiply that by T, which is 8. All right, well, 16 divided by 2 is 8. 8 times 8, last time I checked, was 64 meters, and that is going to be which direction? West. Okay. Let's look at some manipulations of this formula here. Any questions on how that one works? Okay. This is the one we'll use the least. Okay. Believe me, we'll use this one very, very little. Right? But it's important to know how it works. All right, so let's look at this thing set up like this. Vi plus Vf over 2 in brackets multiplied by t. All right, let's say I want to solve for t. What do I do?
Times by T and multiplied by D.
Times by t. Okay, but if I multiply by t, what will I get?
You want to divide by T and then times by D.
Okay. So if I divide both sides by t, like so, what do I do with d now?
You want to go D over.
Okay, but if I do that, if I divide both sides by d, I'm left with,
I said times by D.
hmm?
Times by D. So you get rid of the D in total.
But multiplying by d won't get rid of the d. It'll make it squared. It's on the top. Yeah? Okay, so here's the trick. Nobody likes doing this. That's why very rarely I ever get the right answer for this. Okay? Because nobody likes to say that they can do this, even though they can. This is in brackets, right? Would I do it first? Is it then just one number? Can I divide one number over to the other side? I can. I just got to divide this whole thing over one step. Okay? I can take it all together because the brackets tell me you do it first anyway. Okay? So I can move the whole thing over. Okay? D over V, same as when I manipulate V equals D over T, right? Okay? D over V, so it's going to be VF plus VI over 2, still all in brackets. But now I've left T by itself. Okay? It is absolutely okay to take more than one thing at a time if they're enclosed in brackets, okay? Or if the rules of order of operations, okay, tells you can do that whole dead mass thing. All right, what if I wanted to solve for either one of the V's? What should I move first?
This is where we move the T first.
This is where I want to move the t first, absolutely. So I'm going to divide both sides by t. With that t gone, there is now no need for the brackets. Okay. Now what? What do I do with the 2? Okay. 2d over t equals vi plus vf. All right, let's say I want to solve for vi. What do I do with vf? Subtract it, right? If I wanted to solve for VF, I just subtract VI. They're being added, so I'd subtract either one of them if I wanted to move them over. Okay, so that's all there is to manipulating that formula, right? So our algebra muscles are probably a little atrophied, and we are going to have to work them out a little, okay, here over the next couple of days to get it back in shape again. Okay. I want you guys to try these two. They involve that formula. for the second one, direction matters. Okay, because you've got an up the hill and down the hill in that one. So for question number 1, okay, so we have this hound running at a velocity of 16 meters per second south, slows down uniformly to a velocity of 4 meters per second south. So they gave me VI and VF in that order, okay? They said VI was 16 meters per second south, VF was 4 meters per second south, and they did that in 4 seconds. So again, I don't need to manipulate here. It's already set up to calculate that if I use this formula. Okay, all I have to do is plug in my numbers. So 16 plus 4 divided by 2, okay, multiplied by 4 seconds. Okay, so 16 plus 4 is 20, over 2 is 10, times 4 is 40 meters south. Right? How important is the south? Very important. If you don't write it, you get it wrong. Okay, gotta have a vector on a vector quantity. Okay, speaking of vectors and vector quantities, direction's important in number 2 because VI and VF are opposite, which I represent how? With positive and negative, right? Okay, so a ball moves up a hill with an initial velocity of 3 meters per second. So what I write in my givens, I don't put the positive on yet. 3 meters per second uphill. Okay, VF is 9 meters per second downhill. Right, and that happens 4 seconds later. This is something I don't like about what this book does. How many significant digits does FOUR have? I don't know. It doesn't tell me how it was measured. It could be 4, like 4, or it could be 4.0, or it could be 4.0000000. I don't know. They wrote it as a word. Okay? You never write a number as a word. That's for English. This is physics. We write numbers as numbers. Okay? I have to assume that was a counted number. Okay? Since they don't tell me how it was measured, I have to assume it was counted. And counted numbers do not affect my significant figures because I'm always 100% accurate when I count something. There was 1 1,000, 2 1,000, 3 1,000, 4 1,000 seconds. Okay? I was 100% accurate in my counting of seconds. Okay? Like Monty Python's holy hand grenade. Okay? 3 shall be the number of the counting, and the number of the counting shall be 3. Except in this one, it's 4. Okay? All right. So my time is 4 seconds. Okay. So I have to calculate the displacement. Now that I've got opposites on there, what I often do is I just go negative down, positive up, and then I remember that for later. Because my answer, right, I don't want to write positive or negative. I want to write uphill or downhill. So we're going to have -9 plus +3. Actually, I don't need to write 2 positives there because that looks ridiculous. -9 plus 3 over 2 multiplied by 4. All right, what's -9 plus 3? -6. -6 over 2 is -3 times 4, -12. Okay, now my final answer is not going to get written that way. My final answer is going to get written this way. 12 meters downhill.
Do we just assume that it's uniform? Because obviously you did a uniform example
Mhm.
for motion.
Yes, in this one they should have said
Just
that. Yes, but when you're going down a hill, like for a ball.
trust it? instead?
Yes, you have to kind of trust it. It's also a situational thing. Like, in the perfect physical world, if I set a ball on an incline, it accelerates uniformly. Because it's a ball, not a octagon or something, right? Like it's gonna, everything about it should be uniform. But you're right, it doesn't outright say that. I have to kind of get that from the context. All right. What if you wrote 12 meters down? Would that be right? No. Down is straight down. This is down a hill. It's different. I know that seems really anal, and it is. That's physics. Okay? Down and downhill are two different directions. Okay? Down a hill is at some angle off from vertical. Down is vertical. Okay? So they are different. Make sure you're always saying down the plane, or down the incline, or down the hill, okay? When implied that. Okay? All right. Copy this example down, and we'll talk about the formula that goes with it. All right. So again, getting the context out of a question is important. Okay, so reading it and then kind of deciding on your givens and then thinking or visualizing the situation is an important step. So we got a golf ball that's traveling at 25 meters per second, hits a sand trap and slows down. Right? Which direction is my acceleration then? Positive or negative? Negative. Okay? This ball is slowing down, so its acceleration is negative. Okay? So acceleration is negative 20 meters per second squared. Find its displacement after 2 seconds. All right, so its acceleration is negative. Does that mean it's going backwards? No. Okay? The last time I've played a lot of golf. I worked at a golf course all through high school and university. I never saw a golf ball go backwards in a flat sand trap. Okay, now if the sand trap went uphill, then that was different. It could roll back. Okay, but in a flat sand trap, I never saw a golf ball reverse. Okay, nobody can spin a ball like that. They can do that on the green, but not in the sand trap. So I have to understand that, yeah, when a ball hits a sand trap, it slows down. Okay, sand is resistant. Okay, so it slows it down, but it still continues to move forward. It doesn't bounce backwards off the sand. Okay? So I have to write down my givens. Initial velocity is 25 meters per second. They don't outright say this because they don't ever give us any directions, but they gave us a negative, so I have to write that this one is positive. It was traveling forwards initially. Nobody hits a golf ball backwards very often. And our acceleration is negative 20 meters per second squared, and the time is 2.0 seconds. We're looking for displacement. All right, what formula am I going to use with those givens? Here.
D equals VI times T plus 1/2 A times T squared.
Right. Okay, got to use this formula here. It's the only one that I have all the pieces of information for. I have time, I have VI, I have A, and I'm looking for D. So this formula can do that. All right, do I need to manipulate? It's already set up for D, right? So I don't have to move anything around. I just need to plug in my numbers. All right, so VI, they said, was 25 times the time, which was 2 seconds, plus 1/2 times negative 20. That's crucial. You'd be surprised how often people forget to put a negative in this formula when it applies to A. Okay? And then multiplied by 2 squared. All right, for this one, punching it into your calculator, order doesn't make any real difference here. It's going to do it right. Okay, 25 times 2, okay, plus 0.5 times negative 20 times 4. All right, so it's going to move 10 meters, and that 10 is going to be positive or forwards, okay, on this particular question. Okay, does this one look like it might be a little trickier to manipulate? It can be. But let's have a look at how we would manipulate it. All right, let's say I want to solve for VI. What would I move first if I'm solving for VI? And I'm thinking here of moving a group. Yeah, the 1/2 AT squared. That's what I would move first. Okay? Given order of operations, which is what we just did, I would multiply VI times T, I would multiply 1/2 AT squared, and then I add them together. right? So I can move that whole group, the 1/2 AT squared, over to this side by doing what? Subtracting. Right. So I'm going to have d minus 1/2 AT squared equals VI times t. Still need to get VI by itself. What do I have to do with t? Divide. All right, here's where people sometimes make a mistake now. They divide that side by t, that part they do fine. Then they put t over here, and they go, oh, there's a t on the top. I can cancel. No, you can't. Okay? Why can't you cancel? Not so much that it's squared. I mean, you could. Like, if you had just had t squared over t, it would be t, right? T, like anything squared divided by itself is itself. But in this case, you have another operation going on up top. Okay? If these numbers were all being multiplied, you could then cancel. But because there's a subtraction operation on the top, I can't cancel that. Okay? So I have to punch this in as it exists there. And that'll calculate VI. All right. What if I wanted to calculate acceleration? What would I move first? Very similar to what we did on the last one. The VI times t, how would I move it? What am I doing with it right now? Adding it. What's the opposite of adding? Subtract, right. Okay, whenever we want to move something, we do the opposite. So, d minus VI times t equals 1/2 AT squared. So it's just like the first one. Instead of subtracting 1/2 AT squared, I subtract VI times t. All right, I want to get a by itself. All three things are being multiplied here, so what do I do with the half and the t squared? Divide them over. Right, now I'm solving for a. Right, all I'm doing, guys, is following those three magic rules of algebra. If I want to move something, I do the opposite operation. What I do to one side, I do to the other, and I move what's not attached first. Those three rules got me through university physics. Okay, you too can master the three rules of algebra. All right, here's the tricky one. And you're probably going, really? Those weren't tricky? Okay, this is the tricky one. How do I solve for t? The answer is factoring. No, exactly. Yeah, my thoughts exactly. I hated it too. Okay? You're lucky. Since this is a 20 level course and we can't guarantee that you've taken Math 20, when you take it, you don't have to solve for t unless VI is 0. If VI is 0, what happens to VI times t? It's gone, right? Okay, so if VI is 0, this disappears, and you could then be asked to solve for t, because now it's not involving factors. Okay, so how would I get t by itself in this situation? Divide the half and the a over. Okay, that solves for t squared. I just want t, so that's when you would only be asked to solve for t with that formula if VI is 0. Okay, it is of course possible.
That'd be pretty much the same as the first formula, because we probably have to know it for 6.
For the first formula. The a equals VF minus VI?
When we were just doing, we manipulated it, but you just removed the part where, is it VI? Yeah.
Oh, okay, yes.
VI was 0. If it wasn't 0, would it still be somewhere?
No, it looks a lot different. Yeah. I can show you, but I didn't walk myself through it this morning. Usually before I teach this lesson, I walk myself through it and I didn't do it. So it would take me a long time. Let me do it tomorrow when I've practiced it, because I'm also not very strong in that. Okay. Yeah. All right, everybody okay with that? Okay. Let's look at Okay, you guys try these two, okay? You're not going to have to find time with either one of those, but watch out for this. Well, converting minutes to seconds isn't too bad, especially when it's just 1 minute. Okay, just know that you got to convert that. All right, so the formula we were just using, okay, for these two questions. So for question number 1, okay, skiers moving down a uniform slope at 3 meters per second. So that is probably VI. Okay, the acceleration down the hill is 4 meters per second squared. Okay, same direction, down slope. Find the skier's displacement after 5 seconds. Okay, so only formula I have that has those 4 things in it is this one, and it's set up nicely. I don't have to manipulate it, at least for question number 1. So I already set up to find D. So all I have to do is plug in my numbers. D equals 3.0 times 5 plus 1/2 times 4 times 5 squared. Right? When I do that, I should get 65 meters, okay, down slope or downhill. Questions on the first one? All right, for our second one, we got 100 kilometers per hour, and we got time in minutes, and we got acceleration in meters per second squared. What do we have to do with the 100 kilometers per hour? Divide by 3.6. Yep, we have to do that first. So VI is going to be 100, it's like 27.7 or something like that, right? Divided by 3.6 at 27.77 meters per second, and doesn't tell me which way, so I'm just going to say that's positive. Okay, applies the brakes at 0.8 meters per second squared. What does that tell me about my acceleration? If he applies the brakes, it's negative, exactly. And it's little details like that that we have to get from the context of the question. That's what I mean by there's some reading comprehension here. Okay, for 1 minute. So time is 60 seconds. How far did it travel? So we're looking for D. Right? Again, we don't have to manipulate, but we do have to make sure that we take direction into account when we use this formula. So VI is going to be our 27.7 times 60 seconds plus 1/2 times negative 0.8 times 60 squared. So we punch all that in. Okay, we're going to take that number as it is, multiply it by 60. And then add to that 0.5 times negative 0.8 times 60 squared. All right, so it's going to travel 2.3 times 10 to the 2 meters. Yeah, we only have 2 significant digits here. So 2.3 times 10 to the 2 meters. It asked how far, so that's distance. I don't even have to put a positive on it. All right, questions on that one? Okay. Your quiz for tomorrow will post at 3:30 today. It's just on D equals D over T and graphing, okay? None of this stuff that we learned today. Tomorrow, we're going to go through the last 2 formulas that we didn't get to today on acceleration, and then work on some problem solving. And then we'll be looking at probably doing a lab on acceleration later this week. Okay, so that is the plan going forward. Okay, make sure you try those quiz questions tonight at home. They won't take you very long.